So today we are going to discuss on a very important topic, and that is all about a high performance world of blast furnace productivity. So we are going to perform a deep dive analysis of the principle and technological evaluation that allow us to achieve world class indices in the modern iron making. So let's get started by looking at where this journey began. So, as you can see in the slide, the century of steady growth from 1860 to 1960, or a story starts in mid 19th century. Between 1860 and 1960, we saw a period of a steady mechanical evaluation where furnace diameters grew from under 1 meter to 8 meter. And daily production, if we talk about that, climbed from a modest 25 ton hot metal to roughly around 2000 ton hot metal. But we were eventually throttled by the mechanical limits of that era. So that's all changed with the technological explosion of the modern age. Now, coming to the era of high capacity giants, 1960 to till present. Uh, uh, Fast forward to today, and the scale is simply uh, mm, breathtaking. Since 1960, rapid expansion, pioneered largely in Japan, has given us the furnace with a 15-meter hard diameter and working volume up to 5,500 meter cube. And these monsters are pushing out a staggering 10,000 to 12,000 ton hot metal per day. But to keep these giants healthy, we have to master the mathematics of the process. So the so the mathematical heartbeat, that is productivity, P is equal to Q by K. This is how it is getting defined for our success. It is the equation, as we have already referenced, P is equal to Q by K, where productivity is P, and a direct function of your driving rate Q, the total carbon burned at the 2 year, divided by your coke rate. So to win the game, we must maximize the gas generated at the 2 years while minimizing the gas required per unit of iron produced, all while maintaining a standard 87.5% carbon content in our coke, which is a standard reducing equivalent. So, coming to our next slide about a performance targets and throughput dynamics. Now, let's look at the target. Uh, Modern concrete targets are complex function of net burden weight, limestone, and your ratio of sinter and pallets also. So as you can see from our data, there is an aggregate steps increase in coke plus oil throughput as hot diameter expand. To sustain this, our aerodynamic must be flawless, which brings us to burden preparation. So, mastering our aerodynamics and fines control, as we can see, the permeability is our best friend. Uh, and high production rate. High production rates absolutely demand uh, mm, that we maintain sustainable stock permeability. So we know that fines smaller than 6 mm are ultimate enemy of the gas through flow. By strictly screening this out, we can keep the furnace breathing at high velocity, settling the stage for more advanced charging strategy. So, coming to the strategic charging for pressure optimization is one of the biggest challenge, and how to meet that, uh, that is more important. So, to further reduce our pressure drop, we utilize layer charging and graded burdens by charging different ore sizes in separate layers. We optimize gas utilization and can actually boost output by fantastic 30% to 40% while slashing coke rate by up to 20%. We have found that the pressure drop is at its absolute lowest when the bed consists of uniform material sizes. Uniform material sizes are more important. Mm, so the agglomeration advantages, let's talk about our super material like sinter and pellets. And these are the ideal BF charges because of their incredible mechanical strength and high reducibility. So we can ultimately say strength and reducibility are the two characteristics that coming to play for higher productivity. Superflush sinter are also particularly helpful because they narrow the softening and melting zone, and which leads to a lesser pressure loss in the wet zone, which facilitates smoother gas flow. So just look at the Armco results moving to 100% pellet operation just in preceding slide as we shown. 100 operation nearly doubled their daily production. So coming to the coke, the mechanical skeleton, this is the most important part. So while the ore melts, the coke must stand strong. As we all know, the coke bed provides the mechanical support for the entire stock. So we must prevent coke breakdowns to ensure gas flow in four critical regions: the softening melting zone, the dropping zone, the combustion zone, and the hearth. So if the coke fails, metal viscosity increases and productivity plummets. So we keep it strong. As far as the high top pressure is concerned, uh, the productivity, uh, mm, we can say the productivity turbocharger wants to go even faster. So enter high top pressure. High top pressure is essential for modern large diameter furnaces because it decreases linear gas velocity. This allows us to pump in a much higher blast volume without the risk of bed fluidization. It effectively expands the active portion of the hearth, pushing our capacity towards that 135% maximum index. Now, mm, so coming to the most important slides which navigate our cohesive zone and other area. So to stay at the peak performance, we must manage our limiting factors like flooding, alkali buildup, and scabbing. So we prefer an inverted V cohesive zone because its thick, permeable central coke layer allow for superior gas distribution also. So using ballast top and movable armor, we can selectively charge material to optimize this internal state and maintain a happy, stable furnace. And as for the mm, future discussion and summary as concerned, in summary, we can say that achieving world class productivity is a symphony of narrow size fraction. Number one, flux agglomerates, center, palette, high top pressure, and precise cohesive zone control. So by mastering these variables, we ensure our furnaces are just big but incredibly efficient.